Hi, my name is Aman Bakhta, and today I'll be completing a spectrophotometry simulation for my AP Chemistry class. The goal of this experiment is to apply Beer's law in spectrophotometry to determine the concentration of blue dye in an unknown substance. To do that, I'll first make a calibration curve using standard solutions with the known concentrations and then compare the unknown's absorbance to that curve. Spectrophotometry simply measures how much light a solution absorbs. Since different substances absorb specific wavelengths of light, this technique allows us to identify or quantify them. In this case, the blue dye absorbs strongly at one wavelength, making it ideal for this analysis. We'll be doing this by preparing a series of standard solutions with the known dye concentrations. We'll be able to observe that the solutions with more dye absorb more light. We'll record these absorbance values and use them to plot a calibration curve that visually represents Beer's law. The resulting straight line will show that absorbance increases directly with concentration, exactly what Beer's law predicts. This proves that the dye behaves predictably when interacting with light. After establishing the linear pattern using our standard solutions, we'll follow the same procedure for an unknown sample drink. Because the unknown's absorbance falls on our calibration line, we'll use the slope line to calculate its concentration. Overall, this experiment demonstrates how spectrophotometry provides accurate quantitative information and why it's a widely used analytical technique. I'm going to be starting by preparing the dilution series. I have several test tubes that contain different dye to water ratios: 10 over 0, 8 over 2, 6 over 4, 4 over 6, 2 over 8, 0 over 10, which are blank, and it only contains water. Creating these dilutions will allow me to work with the known concentrations. These standards form the foundation of the calibration curve, which lets us apply Beer's law accurately. I begin by pipetting into the 8 over 2 tube, and since this tube contained less total dye, I added distilled water afterward to reach the correct dilution. I'll be repeating this step for the rest of the tubes, adding less and less of the stock while adding more distilled water. And the last tube is the blank, containing only distilled water. Now I'll be zeroing the spectrophotometer by filling the pipette with a blank sample. I filled the cuvette with the blank solution, and now I'm going to add it into the spectrophotometer, and this ensures that the instrument ignores any absorbance from the cuvette itself or the water, so only the dye contributes to the measurement. Since each tube contains less and less dye than the one before, the spectrophotometer will detect lower and lower absorbance values as we progress. Whenever I inserted the blank into the spectrophotometer, I clicked 0, and this set the baseline for every measurement we're going to take afterwards. I removed the blank solution, discarded it, and now I'm going to be rinsing the cuvette so it's ready for the standard. This also prevents cross-contamination if you're doing this in person. Now I'm going to be measuring sample 1 by filling the pipette. Now I'm going to be putting the cuvette into the spectrophotometer and clicking measure. As we can see, the instrument gives us our first absorbance value, and the data point appears on the calibration graph. This one reads 0.49, 49%. I'm going to be pouring out the solution, rinsing the cuvette, and repeat the process for the rest of them. I'm going to make sure to rinse the cuvette each time so I prevent cross-contamination. Now I'll be measuring the blank again, filling the pipette with 3 milliliters from this tube. I'll be dispersing the blank solution into the cuvette, and now I'll be clicking measure, and our spectrophotometer should be showing 100%, confirming that our 0 point is still correct. Now I'll be emptying the blank cuvette into the waste. I'm going to make sure to clean the cuvette just like before, and now I'll be measuring the unknown solution. Now I'll be grabbing some from the unknown, putting it into the cuvette, measuring, inserting it into the spectrophotometer. Now I'll be clicking measure to, to obtain the absorbance of the unknown sample. As we can see, it's 39%. Now our experiment is complete. Now we'll be doing our data analysis. Using the slope from the calibration curve, I now calculate the concentration of the blue dye in the unknown drink. This step applies Beer's law using the values collected earlier. Here is the completed data table, which includes dilution ratios, concentrations, percent transmittance, decimal transmittance, and absorbance. My percent transmittance values ranges from about 49% at its highest to around 87% for the most diluted sample. The blank is excluded because it's only used to zero the instrument. To convert the percent transmittance to decimal form, I divide by 100. Then I calculate the absorbance. Absorbance values decrease as the dye concentration decreases. These values are used to generate the calibration curve. The graph forms a straight line, which confirms that the dye follows Beer's law. The slope of this line is 0.1358, as we could see right here. And the unknown solution percent transmittance was 39%. To calculate the concentration of the unknown, I plugged the absorbance into the line equation and divided by the slope. Concentration equals absorbance divided by slope, which the absorbance in this case, which was 0.4089 for the unknown, and divided by the slope, which was 0.1358, which approximately gave us 3.011 for the unknown drink's concentration. By completing this procedure, we demonstrated that spectrophotometry is an accurate method for determining the amount of dye in a solution. This experiment reinforces that absorbance increases with concentration, and the calibration curve is an effective tool for analyzing unknown samples. Thanks for watching, and I hope this walkthrough helped explain how spectrophotometry and Beer's law work together to determine the concentration of a substance.